I must say from the beginning that this is going to be a highly technical presentation. I was a lead researcher on behalf of the country at the FAO, GSP. I don't know if you know about GSP. It's called Global Soil Partnership. It is housed at FAO in Rome. So I think it is advisable that you just Google them and find out what they are doing, because there is quite a lot of stuff that is happening there. So we had this project of mapping salt-affected soils globally. So I was the guy from South Africa who was representing the country. So I'm going to share a little bit with you on the protocol. And yeah, I hope some of you will take it forward and develop some interesting products. If you look on this slide, this image is not looking so good. And this was taken in Bangladesh. This area is impacted by a high amount of soluble salts. So what the salts do, the salts do to the soil is that they increase the osmotic pressure. And as a result, your crops or your plants will not be able, will struggle to absorb the nutrients and the water from the soil, and eventually the land will become bare. And we know all these degradation issues that are associated with bare soil. So we wanted to just know where is this where are these salts concentrated in the country. So a little bit of background, as I've already indicated, salt-affected soils are soils with a high content of soluble salts and or sodium ions. Now, what we did for us to model this issue, we used spatial modeling based on the digital soil mapping concept. I think I don't want to say a lot that it involves a lot. The top plus first law of geography. Those of you who are familiar with geography, you know that that guy said nearer things are more related than far away things. So there is a variogram there to understand the relationships between if you have a point here and another point 2 meters away and another point a kilometer away, the one that is 2 meters, there might be a strong relation compared to the one that is 2 kilometers away. So that is one thing. And then he also Alex McBride, the guy who came up with this digital soil mapping concept, he conceptualized the whole thing from the soil formation factors. So he came up with a model called Scorpan. So he said soil is a function of, and then it listed all those things: parent material, vegetation, and all that. I think those are the things that we know. So now in this model or in this concept, now we will try to build the relationship between the drivers. Other people call it predictors, or maybe when you read some literature, you'll hear the word covariates, and the indicators of soil problems and all soil forming factors. So we'll try to understand the relationship between all these variables. I will explain this one a little bit later on. So for this study, trying to model salt affected soils, we needed input data. So the most important data set that we needed is soil point data, the georeferenced soil point data. So we needed soil pH, electrical conductivity, and exchangeable sodium percentage. So we needed these three variables the results from, and then the EC was in the form of saturated paste. So that is the first hassle that I had to face. I have to map this issue for the whole country. Therefore, I need a better distribution of these data points. The other important input data is climate raster, because we know that the issue of salt affected soil is also influenced by climate. So, and I guess you have a bit of idea what I mean by a raster. So this is a data set that is having equally sized grids. So every grid, then we need to know what is the mean annual rainfall, mean and maximum temperature. So already under climate, we have three data layers. The other factor is parent material. So we used geology data set, and we also rasterized our land type data. Then we went into remote sensing, and then we used a MODIS data set. So we look at that multispectral data set. So we looked at the visible spectra of the electromagnetic, your red, your green, and blue band. And we also used near infrared and shortwave infrared. Those are the remote sensing stuff. And then we use digital elevation model and another software called Saga to calculate these relief parameters, your slope, your length of slope. People just call it LS factor, or longitudinal curvature, valley depth, and CCNBL. So, excuse me. So these are the parameters that we got from the digital elevation model. And then also we used a land cover raster map. So these are the input data that we needed for this model. So you can imagine already that these are raster layers. So it means this study was massive when it comes to data. So it is a big data study in any case. So you need a computer with a better RAM. Right, so quickly, let me just share with you the commonly used satellite platforms that people use to map salt affected soils. We, as I indicated, let me just, as I indicated that we have this column here that is indicating the region within the electromagnetic spectra. So we have visible, we have a blue, green, and red bands there. So those are the normal things that we are used to, and we know that a healthy vegetation will absorb the blue and the red band and reflect a lot of green. That's what we see. And then we also have infrared. We know again that a healthy vegetation will reflect a lot of near infrared. This is something that we cannot see with our physical eyes, but the remote sensors or guys, or nowadays even guys in agronomy, they use near infrared to assess the crop health. And then of course we have shortwave infrared and 1 and 2. And then we have the first platform, Landsat from the Americans. And then the spatial resolution is 30 meter. Then we have Sentinel-2. This is from the European Space Agency. This is the satellite that is there from the Europeans. And we call it a high resolution imagery because as you can see here in the spatial resolution, you can get from band 2 to band 8 the resolution is 10 meter, which is better compared to the Landsat imagery. But the beautiful thing about Landsat is that you can go as far as 30, you can get data for 30 years. But the Sentinel-2 is fairly new satellite. So I think it was launched in 2017, if not mistaken. Then we have MODIS. MODIS, if you look at the spatial resolution, is pretty much coarse because it is 500 meters. But now the other issue with these satellite imageries is how frequent will you be able to get imagery for the same piece of land. So that is what they call it temporal resolution. So the mode is, in as much as it is so coarse, but you can get imagery of the same place every day. The Sentinel-2 every 5 or so days, and then Landsat you can get imagery every 10 days. So those are the trade-offs that you need to consider when you go into remote sensing data. So and you'll read a lot. I mean, you'll see a lot of people in this field of mapping, whatever the issue. It will either be Landsat or Sentinel-2, but the rangeland guys, because of they want to monitor daily or weekly what is going on with their natural field, most of them they use MODIS, more especially if you do a study at a bigger scale. All right, now the software that you need for this exercise, we were of the view that we need to move a little bit from expropriative software to free and open source software. So as I said, we used Saga to calculate those relief parameters. We have also used Elwis to harmonize our layers. I'll talk about it a little bit later. And then we spend a lot of time in R. That's where we were doing the modeling. That R was the main software. And then QGIS, we just use it for visualization of the results. And in R, those of you who are familiar with R, you need what we call packages. So if you have any type of study, the first thing that you need to establish first is which packages do I need for my analysis. So these are some of the packages that we had to install in R because they are the ones that we used for this study. And then this is just for interest sake how you load them. After installing them, then you load them in R. So you used a library command. This those of you who are familiar with R, you know for sure that R is more scripting. You script, and I think that's why most of people don't like it, because it takes a lot of scripting. But it's quite a very interesting software, and I highly recommend it. Now, with those satellite imageries, then we derived what we call indices. So for me, indices is just mathematical equations, really, nothing much in that line. So if you look at SI1, for instance, you can see that we take the square root of red band multiplied by green band. So then you have that index. And then we had to calculate all these indices in R. Yeah, for sure, you might be familiar with NDVI, because I think that's the most commonly used index in agriculture, where we use near infrared. You take red band and then you divide by near infrared plus red band. So we have those indices, then the whole science that we know, that we study the distribution of your data, and then do a little bit of transformation where the data is skewed. We want to have that bell shape. So we did for all those indices study how is the data distributed and transform where it is skewed, because if it is not transformed, then you might miss some very important information later on when you do analysis. And then after that, then we did a correlation and principal component analysis. The reason we had to do this is because we had to do principal component analysis was that we were guarding against multicollinearity, where you find variables pushing each other. So if you see that these variables are pushing each other, then we took them out of the model. And we were happy to use up to principal component 4 because it was giving us 0.99%, which is almost 100%. Then we eliminated the other ones because it was just noise in our analysis. But I think that is just a little bit of the thinking into or data preparation up to that level. But the first thing then was to you map your soil affected soils indicators, because you can't just measure one thing and say you know the salinity. I mean, you can't say I measured soil pH and then therefore I know salinity, or electrical conductivity I know salinity, or exchangeable sodium. So we are going to do a mapping of each variable, pH, electrical conductivity, and exchangeable sodium percentage. So, but I just picked up one, soil pH. So we are going to use a supervised learning methodology. So it means you give the learning algorithm something, and then the algorithm will learn from that information that you provided. So if you provide the learning algorithm with information that was not properly analyzed in the lab or properly collected in the field, or with wrong coordinates, then the algorithm will use that and learn and then give you something. So the workflow is that you need to load the training data. So those are those georeference point data of your electrical conductivity, soil pH, and ESP. So you know it. We load it into the system, and then the learning algorithm is going to learn from that. And then you train the learning algorithm. And then from there, after training the learning algorithm, you will apply it, and then afterwards, then you assess the accuracy. So normally, what we do, we put if you have, let's say, 5,000 data points, you take 70% and use it to train the learning algorithm. All right, and then the remaining 30% you use it to assess the accuracy. And we use K-fold methodology to assess the accuracy. So you train with the 70%, the remaining 30%, then you use it for accuracy assessment. Other people who have time, like in this case, I think it will be very interesting that after the study, we still go to the field to say, okay, the model said here, you'd probably find soil affected. So you go there and sample again and check if the learning algorithm, how far is the learning algorithm from the truth. All right, so then there is a process of choosing the learning algorithm, because there are so many. If you look on this reg model suite, this is the command that we used in R to choose the learning algorithm, and it took about 2 days. You run it, and then you do other things, and we have a 32 gig RAM desktop where we do our analysis, but it took 2 days. You can imagine if you have 8 gig RAM, it will take 2 weeks for you to just get a learning algorithm. So that's why we need supercomputers, and now a lot of people are moving into computing in the cloud for this type of studies because of computational demand. So you run this line with those up to those variables, and then you'll get this output. These are the learning algorithms: your random forest, a support vector machine, your CAT, your ranger, and so on. And then we're looking at this your mean error and root square mean error. And then also look at your R squared and NSI. So we want your ME and RMSE to be lowest, and we want your R squared and NSE to be highest. So, and most of the time, because we were from all over, Lesotho guys, Zimbabwe guys, and then we were communicating a lot, quantile random forest was performing better. But we realized that for you to use that learning algorithm, it will take a lot of time. Computationally, it is quite demanding. So we opted for a random forest because it was the second after quantile random forest. Then after that, then we use this line. So under this method, if you are going to use quantile random forest, this is where you put it. You say QRF, or if you are going to use random forest, this is where you say random forest. If you are going to use CAT, and then the software then will pick up the learning algorithm that you put. So eventually, then we ran this thing, trained the learning algorithm, and we applied it. And then this is the pH map that we found after the machine learned. You see, we gave it a data points, and then we gave it the geology, the layer, and then in that point to say, okay, here is my pH, I'm pH 7, this is the rainfall, minimum rainfall, maximum rainfall, this is the geology in that point. And then it will try to figure around the whole country, creating relationships and then predicting at the end of the day. So this is the final product of that learning algorithm in terms of mapping cell pH. Then we went again to map electrical conductivity and exchangeable sodium percentage. I know this is, it might sound a little bit foreign, but everything that we were doing up to this far, we were trying to map those variables, those three variables, those indicators of salt affected soils. And then we mapped them. Then we now have to say, okay, what is a saline soil? What is a saline sodic soil? What is a sodic soil? Looking at those three variables. Then other people, they, instead of exchangeable sodium percentage, they measure sodium adsorption ratio. So
sorry, Malatji.
Yes.
Yes, sir. I just wanted to check something. Can you please go back to the slide where you have the map? Okay, I think. Oh, okay. No, I just wanted to see all the values here, the pH values on your legend. So it's 5, 6, 7, 8, 9.
Yes.
Okay. So does this mean that the areas, the coastal areas had lower pH levels?
Yes.
If I, oh, oh,
Yes.
oh, okay, okay,
Yes.
okay.
Okay.
Oh, all right.
So now in this table, and this is the FAO classification criterion. So we say if your pH is less than 8.5 and your electrical conductivity is above 4, and your ESP is less than 15, then that is a saline soil. If it is greater than 8.5, less than, then that is your sodic soil. So that is the first thing. Is this soil saline or saline sodic or sodic? And then we are going to use this based on those three maps to determine that. And then the other issue was the intensity. Is this a slightly saline, moderately, very strong? You know, those things. And then we use there is a FAO and USDA, but we were using FAO standards for saline ECs, like it has to be in these regions, and then for sodic soils, ESP will be in these regions. I think up to so far, I felt it might be necessary for me, because this is, I know for sure, because it took me a month or so to figure out what is going on, and I can imagine me sharing this thing with you in just a few minutes. It is quite demanding, because it is cutting across so many fields: geography, geostatistics, machine learning, you know, soil science, and so on. But the approach is that we need this point data, georeference point data, and then we need these predictors. Other people, they call them covariates. And then the first step, we had to do input data assessment and preparations, you know, those descriptive statistics. And then you later on do harmonization. We harmonize cell depth. We must make sure that all those layers are using the same coordinates reference system, are in the same projection. The spatial resolution is the same, and they cover the same extent. The reason why we need to harmonize this is because we are going to overlay them. So if the coordinate referencing system of one of the layers is not the same, then the software will simply not run. So we need to make sure that they are the same, so that they can be on top of each other nicely. And then, like I said, we then computed the indices, we transformed the data, we did correlation and principal component. This is just part and parcel of input data assessment and preparation. Then the next step, then we did the modeling in R. So you select the model, you train, you apply, and then you assess the accuracy. And part and parcel of assessing the accuracy, because like in the Northern Cape, we did not have a lot of soil samples there. The model will say to you, here I'm guessing a lot, so give me some data. So and that's the nice thing about it. And then after that, then we did the classification of salt affected soils, you know, where the salt affected soils, the intensity, and also the uncertainty. And then we then had a map of salt affected soils. So this is the map of salt affected soils in South Africa. The modeled one, the predicted one, looking at 0 to 30 centimeter. We also did the same process for 30 to 60 centimeter. No, that's why I was saying here one of the things that we need to harmonize is your soil depth, so that you can pinpoint to say, I want in this region. I think that's the powerful thing that the technology is giving us nowadays, that you can zoom into depth of your interest. If you're interested in 90 to whatever, you can harmonize in that space, and then you get. And then what we did so far, we went to Kruger National Park, because we picked up that, oh, what is going on here? And then we went there, and they welcomed us, and then we did a little bit of sampling there, and indeed we found that the sodium, indeed they confirmed that the salinity is an issue. So yeah, okay. So and then later on, then we in QGIS, then we calculated how many square kilometers in each province is moderately or slightly, or whatever the intensity, saline or sodic. I guess I've said a lot, and that's the end of my presentation. I think we can engage from here if there is any clarity-seeking question or any input. But I think what am I saying with this is we get applications through Conservation of Agricultural Resource Act 43 of 1983 of people who want to start irrigation schemes. So we use this data to say, but there is salinity issue in your place. Then you cultivate in that area, it might you might run into problems. Things like that. And I think one way or the other, we are trying to move into a situation where we will be able to monitor the waterlogging and salinity, more especially in irrigated fields, using this technology. I think that's where we are going with this monitoring systems, and we are looking into cloud computing, and that on its own will require us to learn a little bit of Python because it is quite versatile, and a lot of these cloud computing companies are using your Amazon web service is using Python. So I'm a soil scientist, yes, I agree, but the future, I think, with these advances in technology somehow forced me to take a certain stream. It's still soil science, but they call it pedometrics, and yeah.
So thank you very much, Adolph. Sorry, I was speaking with my mic muted. All right. Thank you very much, Adolph. Thank you. That was very, very interesting. From my side, I think I have a few questions, but I'm going to start with I just want to hear from the colleagues here if they have something to say or maybe they have questions to ask. Yes, Vusi.
Good evening, everyone. Thank you very much, Adolf. I think this was very much full and nice combination of different fields indeed. But yeah, everything fitted well perfectly. My concern is I don't know how much knowledge you have of this bioresource unit concept. I know that it's mainly a system based in KZN, but you may probably have some idea about it. So with regards to what you were doing, I'm just thinking along the lines of this bioresource unit concept, even though what you were doing is more advanced than what Smith did. But one of the things that they always emphasize there on that system is that field verification is more than important. So you don't just end up with the desktop work and hope that everything is the same with whatever conclusion your system may be showing. So in your case, how much verification is involved? That is what I'm asking myself right now after listening to what you are presenting. I don't know if my question is clear enough.
Yeah, I think it is in a way, and asking a very important question, and that's why I was saying in remote sensing, and that's why I'm always arguing with them that you see these modeling things, they are prediction, but the main thing is how far is your prediction from the truth. And then that's where the validation process comes in, and that's very crucial. So at this stage, like I was saying, we had 4,000 data points, which is quite small. and we reserved 30% for field validation, and I post these lockdowns, and then I managed to go to Taung irrigation scheme that side in Northwest, and the Kruger National Park. We haven't really done a lot of validation post the study. I mean, when we were doing the study, we used those 30% of almost 5,000 data points, and then only those two sites. So it's a continuous process, and we need to continue. Wherever I get a data point, I'm always looking into what is the pH, what is the EC, and what is the exchangeable sodium percentage. So at this stage now, I'm working with the FAO guys we are building a system where those data inputs, then we'll put it in and then validate our results. So it's a continuous process, but we had to start somewhere.
All right. No,
Yes.
thank you very much.
Thanks.
Thanks, Vusi. I see Idu.
Thanks, Doc. Good evening, colleagues. Again, Mr. Malatji, thank you for the presentation. There's a lot to take in, but it's very interesting nonetheless. I wanted to ask a question, or maybe I'm seeking clearance on EC in soil, the electric conductivity in soil. How was that conducted? How do you measure the electric conductivity? Is it that when the soil is more saline, then it's more conductive or less conductive? So please elaborate on that one. Thanks.
Sometimes I feel I'm not the relevant person. People like Sadique can tell a good story, but you see, this issue of conducting is influenced by a lot of things. So it can be influenced by salts, yes. It is also influenced by clay percentage. So soil which is more clay is conducting more than sandier soil. It could be influenced by also the moisture content. So that's why sometimes when somebody says the EC for this soil is this much, and therefore the soil is saline, and then we'll start to ask, we have to ask questions. What is the texture of that soil? You see, what is the parent material where that soil is coming from? Because it is also having an influence in that. So EC can tell us quite a lot of things, and that's why we can't use it alone. I don't know if I've answered your question, Itu.
I'm answered. Thanks.
Okay.
Thank you, Idu. Vusi, is that a legacy hand?
Sorry, Doc, yes. Sorry.
Okay, all right. No, that's fine. Any other question or comment? Maybe while we're waiting for the comments or questions from the colleagues, Adolph, I think when you were talking about, okay, Mr. Moshala. I'm going to park my question for now.
Thank you so much, Doc. Adolph, thank you so much for the presentation. It was a very interesting presentation indeed. Yeah, but my question is simply to understand the advantages of using this type of approach where you use
machine learning algorithms to predict those parameters, because I believe you can use the same approach even for other parameters, like when you want to test, or maybe to conclude, to say in these parts of the country there is much of maybe, for example, the level of potassium in the field, the level of phosphorus, or so on. Yeah, but I wanted to know what are the advantages of using this approach versus the normal approach where we do like we go to the field, take samples, analyze in the laboratory. Yeah.
Okay.
Thank you.
No, thanks very much. I think the starting point to respond to your question, which I think is quite interesting, is that we can't do without soil analysis in the lab. We still need that, and that's why I was saying that 5,000 data points is not enough. We need more data points where we have values for pH, EC, and exchangeable sodium percentage. So the laboratory is still a very integral part of these advances in technology, because without it we have got nothing. You can't predict without putting in something where the learning algorithm will learn from. Because otherwise we just have those layers, your parent material, your climatic data, your topographical parameters and all that. Then the learning algorithm will have nothing to learn from. So the laboratory results are what will help the learning algorithm, will train the learning algorithm. So I think the first part is that we need the laboratory analysis the most, and I wanted to clarify that one. So, but with this approach, actually, machine learning is an entry into artificial intelligence. So, and indeed, if you Google the definition of machine learning, you'll find it will lead you to artificial intelligence. So, we give the learning algorithm something to learn from, and then it will artificially go to other areas where we did not take soil samples and then predict for us. So now we will have a surface map, and that's the key part, because with the traditional way of doing these things, you go to a spot and you take a soil sample, but how will you know how far that pH goes, that pH value? So with these advances now we have a 1,000-hectare farm, then you can map soil pH, you can map clay percentage, you can map this and that, you can map, you can have a surface layer, and that is the most advantage part of this approach. I don't know if I've clarified your concern or your question.
I'm clarified. Thanks, Malatji. Thank you very much.
Okay, thank you very much. I think I will ask my question now. One of the things that I wanted to check was that I think in one of your slides you spoke about the different classes that you use to identify whether the soil is saline or non-saline or something like that. I think you had the USDA and the FAO categories or classes, and you mentioned that you used the FAO, but not the USDA. The question I had in mind was that why did you use the FAO, not the USDA?
Yeah, I think that's a very interesting question. But I think to answer to that one, because I was talking to one of the guy they call him a guru of soil salinity in South Africa. His name is Dr. Pete Nell. I think he's at ARC, the Soil Institute. He was also saying, but you see that 15 in our context is quite high. But in this project, because it is a global product, so the South Africa did its part, Lesotho, the region, African region, the Americas, and so on. One of the leg that FAO is looking into is on the issue of standardization. So they want us to use the same measure or the same approach. So even the Americans, they pushed them to use this, and they said, but if you want to localize it, you want to input you can use later for your country, then use your own values, so that we have a harmonized way. I don't necessarily agree with that approach, because each country or each region has got its own issues, but for this product, for this global product, we agree that we are standardizing. So, but that is something that is also, continuously developing. If people in South Africa feel strongly that the criterion for FAO is too high for us, we need to lower the values. You see, that is something that we need to now localize it in our context.
Oh, okay. All right. No, thank you. I was just wondering. And the reason one of the reasons I'm asking is because, when you are classifying soils, especially if you're trying to write a paper that you would publish in an international journal, sometimes actually I've seen some of the papers, they would actually use the FAO, classification as well. So that's just one of the reasons I actually asked the question. And then another question I have is, what you spoke about collecting samples. I know you said you went to the Kruger National Park collecting samples and all that. I was just wondering if you worked with institutions that have data, or institutions that have been collecting data, and soils data from these different provinces in the country, because I'd like to believe that there are institutions that have been collecting data. So have you tried to work with them so that you can gather more data you can use for these models?
Yeah, I think you're asking a very important question. It's a very difficult one, because let me just talk about government. But I don't want to mention provinces by name. There is a huge. It's like we are not one. It's like we are federal system. When you go there and ask for data, it's not easy. They will send you from pillar to post. So other people will talk about, we have used our budget to collect this data. What are you giving us in return? But then, okay, I argue that, but the product that I'm going to generate will also benefit you. So I don't know, maybe in academia it's easier to just go and knock in a department and access data, but it's not that simple. I had a huge struggle actually with ARC, because we see them as the custodian of soil information data, and the 2,000 data points we did get from them, and then we had to use other sources. So I think as a profession, we need to come together somehow, one way or the other. And one of the issues is that component, or how can we share data? And I think we need to work on that. I'm trying from national to formulate a soil science technical working group, and that is another subject that we will need to address, because indeed it's not easy to do this kind of studies without data. And by the way, these kind of studies, because that guy I spoke about, Alex McBride, the one who came up with that Scopan model, he's actually the guy behind precision agriculture. So you can do this at a farm level, when you have a 200 hectare farm and you want to, manage your nutrients using such specific technology. So it's the same concept. It's just that this one is now at a higher level. So the data issue, I think, is just something else that needs to be we engage robustly on it to see how best can we work around it. And unfortunately, some of the labs, unfortunately, they don't. When they do have data, but it's not georeferenced.
Yeah, I see. Yeah, and I actually understand because especially if it's a commercial laboratory, because I mean they get receiving samples from farmers, and some of the farmers will not even collect, would not submit the GPS coordinates and things like that. When they're submitting the samples, it does happen. Okay, I hope I'm not going off the tangent. All right, no, thank you. One last question. I mean, after doing the work, this wonderful work you have done, the question I have, would you say, I mean, I'm just thinking, if let's say I'm a farmer and I know nothing about the technical work you have done, but the only thing I'm looking for is, can we say we have a problem of what? Salins of soil salinity or soil sodicity in South Africa? Is it something I should be worried about if, let's say, I'm a farmer in South Africa? And if it is, which parts of the country where you would say they are more problematic? If that makes sense to you.
It makes sense. Yeah, it's got a very interesting one. I mean, we found out that the key drivers of salt affected soils. Actually, we have two types of salinity. The primary salinity, the one that is naturally occurring. That one, it was not influenced by us, our own doing, but this is happening. And we found that climate and parent material are the main driver of that one. The primary, the naturally occurring one. So yes, if you are in areas, actually the guys who were developing these irrigation schemes, they were taking they were meticulous when it comes to that, to say, no, irrigation schemes, by all means, we don't want to go to areas where naturally the soils are salty because of parent material and the rainfall. So you better choose other better places where that naturally there is no that problem. The other issue, or the other type, is the secondary one that is mainly influenced by our activities. Mining is one of them, fertilizers, irrigating with borehole water, which is salty, and all that. So to answer your question, normally where it is naturally occurring, you find that a lot of those places are used for just a natural felt, it's a rangeland. Or other farmers will try, more especially the small scale, because we don't have necessarily that knowledge. But the commercial guys, they are fully aware of this issue because it is impacting on the productivity of that land. So, and they tried by all means to shy away from that. And then when they irrigate, what type of water are you using? Is it not adding salt in your soils? Farmers are now becoming more concerned about that. Yeah, so the main thing at the end of the day is how do you manage? Okay, what do you know about your area, and then how do you manage so that you don't increase or you don't initiate a problem where there is no problem? I don't know if I answered the question, but we from our side, we wanted to know the footprint. Where do we have this problem? And then now there are people who are saying, but we know there are crops that are tolerant to salt affected soils. They are busy putting the thinking together to say, we can put this crop, or we can put this type of a grass there, so that the whole thing of carbon sequestration comes back, so that we don't leave it bare. So it depends. The problem depends on where you are.
Yeah, no, I see.
Yeah.
Because one of the reason I asked is that I actually expected areas like I mean, just from the top of my head, I was thinking that maybe provinces like Northern Cape. I know you mentioned that you didn't get many samples from there, but I was actually thinking that that province would have more salty soils or something like that. Maybe, for example, in comparison with I don't know, Limpopo, KZN, or Mpumalanga, I don't know.
Yeah, maybe if you don't mind, let me just share that map again. I don't know if it's there. Can you see it?
Yes, I can see, but it's not on slideshow.
Okay, let me. Is it visible?
Yes, yes.
Yeah, so that is your Northern Cape, how it looks like. Yeah.
All right. Okay.
Yeah.
No, thank you. Thank you.
Okay. All right.
That's it from my side.
All right. No, thanks a lot, guys. But I think the take-home message is that soil science alone, we need to integrate other disciplines, because alone the world is moving at a very alarming rate. So and technology will be part of the future by the look of things. I'm not necessarily saying I'm correct. Then we need one way or the other to think along those lines.
Yeah, I think you're 100% correct. No, thank you so much, Adolph. I think that was wonderful talk. Actually, it's very, very, very informative. I learned quite a lot. So I think we have actually gone over our time. Colleagues, I just want to thank you for the conversation we had. Thank you so much for the questions and comments and your presence. Thank you so much. I think we have come to an end of our webinar for tonight. I can say have a good evening and enjoy the rest of the week. Yeah, thank you so much.
Yeah, no, thanks. We are busy with the manuscript, and very soon we want to publish this work in the Nature journal. So once it is through, I'll let you know. Yeah.
Okay. No, thank you so much. Thank you, colleagues.
Thanks.
Have a good evening.
Bye.
Thanks. Bye.
Thank you.
Bye.
Bye-bye.
Have a good evening.